Here, the part 2 of Hadlow's chapter is mainly about discriminant of flow region and the relationship between the internal friction stress and the frictional Hadlows. In the Reynolds experiment, we take the left point of transition zone to be the critical velocity Vc that discriminates laminar and turbulent. People found Vc is proportional to the value of viscosity divided by density times the tube diameter, as the upper relational expression shows. However, to find Vc is not easy and convenient in practice. The good news is the value of proportional factor, it is the Vc times diameter d over kinematic viscosity nu, is always about 2000. So, a criterion number named the Reynolds number Re is defined by the expression in the page, where V is the sectional mean velocity in the tube and nu is kinematic viscosity of the fluid and the d diameter of the tube. Thus we can find the flow region in a certain tube by the comparison as written with the red words. Maybe in some textbooks you see the criterion is 2300 or 2500. It's okay, there's no essential difference. It belongs to personal preference. Let us to see how to find the flow region. This is an example. From it, we know that the more viscous or thicker the fluid is, the more likely it's laminar. Why? Here we leave a question to be answered. Pay attention to that the critical value of Re being 2000 is just for circular tube flow. If the cross-section is not circular, the Re expression should be as V times R over nu, where big R denotes hydraulic radius and equal to section area A divided by wetted parameter kappa. As an example in the picture, the wetted parameter is the red line for trapezoidal section. Hydraulic radius is not the real radius, but a one in hydraulic sense, and it can reflect a kind of effect of boundary on fluid. So, for non-circular section and the definition of such expression, the critical Re is 500. This value doesn't conflict with number 2000 for circular pipe. Here's an example of flow with non-circular cross-section. The red line in the picture is the wetted parameter. Reynolds number Re is a dimensionless number. You can analyze by yourself. Its physical sense lies in the ratio of inertial force to viscous force. You can see that by dimensional analysis shown in the page. So, if it's smaller than 2000, that means the predominant force is viscous force. In such cases, viscous ability of fluid can be able to restrict the inertial behaviors of the fluid particles. Thus, the particles are moving on each layer regularly. So we can see the colored line in Reynolds' experiment being able to maintain all the time. This is a laminar. If Re is larger than 4000, that means inertial force is overwhelming, and the particles are able to get rid of the viscous restraint and escape to other layers randomly. So we can't see the color line anymore. We just see the color has been mixed up to all flow space. This is turbulent. Now that in turbulent flow, the particles travel path at random, how do we classify flow by the concepts we have learned before? Don't worry. Despite that the transient movements of particles are chaotic, their timely average behaviors still conform to those flow definitions. That's to say, we can determine the type of a certain turbulent flow in sense of time mean, such as steady or not, uniform or not, one-dimensional, two-dimensional, or three-dimensional. So, in later learning on our class, unless otherwise specified, we refer to time average current. We have known that heat loss results from internal friction, or in a more standard statement, shear stress. Then, how is their relationship? We take steady uniform flow to find, because such kind of flow is the simplest and its acceleration is zero. Either pipe flow or open flow, such as in the picture, we can analyze the forces on the control volume between section 1 and section 2 and write the force balance equation along the current direction. In the picture, alpha is the slope of pipeline. Tau naught is shear stress on the side boundary. P1 and P2 are pressure force on the cross sections of upstream and downstream, respectively. G is gravity force of the control volume. So in current direction, there are only tau naught, P1, P2, and a component of G. From the piezometric head tubes, we can learn frictional head loss of the flow ridge between 1 and 2. Please note that the pressures on sidewall are normal to the wall, thus the pressure force is zero in current direction. So the balance equation is written like this at the bottom. We rearrange the equation and then have such deduction process in the page. Pay attention to that we didn't involve the flow region in our deduction, so the result can be applied to both laminar and turbulent. Now we see wall shear stress tau naught is equal to specific gravity gamma times hydraulic radius r times energy slope j, which is head loss on unit flow length. This is the relationship of shear stress and frictional head loss. It is also called basic equation of uniform flow. Why is wall shear rather than internal shear? It's because, first, boundary wall is the direct factor to resist the current, and second, internal shear is somehow related to it. Look at example 3. Whenever a problem involving boundary shear tau naught is referred to, we should think of the uniform flow equation tau naught is equal to gamma times r times j at once. Here, we should pay much attention to a differential manometer in uniform flow, where the piezometric head difference is exactly the frictional head loss HF. And a mercury height in such manometer should be transformed to a water height with a conversion factor 12 0.6. With a similar deduction, we have internal shear expression as the equation on the top in the page. In the expression, R' is the hydraulic radius of flow beam shown in blue in the picture, and the tau is the shear stress on the beam. Then we have shear stress distribution on the cross-section expressed by the equation on the lower. It's linear as shown in the picture. The maximum value is on the boundary, while the minimum is 0 at the center for pipe flow and on the free surface for open flow. If we combine these three equations, then we have relationship between boundary shear stress tau naught and the mean velocity v by defining a friction velocity u star. So u star is not a real velocity in the flow, but a quantity in speed unit to represent shear stress in some way, or resistance to some extent. We can see in the bottom equation that the faster the current, the more resistance it has. Like our people, the faster we run, the more against wind we feel. This is an example for calculation by U star to solve a problem. Now let's take an insight of laminar flow. Combining these two equations, among them dependent variable is point velocity u, and independent variable is radius r, which locates the point. Finally, we have the velocity distribution on cross-section of laminar flow. It is a parabolic distribution. Now that we have velocity distribution, we can deduce mean velocity as in first line, flow rate in second line, frictional head loss in third line, and the maximum speed at pipe center on bottom line. Especially, we find that for laminar flow, friction head loss coefficient lambda is equal to 64 divided by Reynolds number Re. So simple, so easy that we should keep it in our memory. This is the end of part 2 of the chapter.